Hello again. In this video, we're going to discuss the relationship between continuity and differentiability. So Theorem 3.1 says that if f is differentiable at A, then f is continuous at A. So I'm going to prove that theorem. So let's suppose f is differentiable at A. Now remember, f being differentiable at A simply means the derivative of f of x exists at A. And what we're going to show is that f is continuous at A. And the way we're going to show that f is continuous at A is we're going to show that the limit of f of x as x approaches A is the same as f evaluated at A. And that's the very definition of f being continuous at A. Okay, so if we can show this, show that these are equal, then we've proven that f is continuous at A. Now, the way we're going to do this is we're going to take f of x and we're going to rewrite it in a very special way. So f of x is the same as f of x minus f of a divided by x minus a times x minus a plus f of a. Now let's see why this is true. Notice the x minus a here and the x minus a here cancel out. And so you're left with f of x minus f of a, but then you add f of a to that, and the f of a's cancel out, and you're simply left with f of x. So f of x is equal to this. Now there's a reason I'm writing it this way, because now what we're going to do is we're going to take the limit of both sides of this equation as x approaches a. Okay, since f of x is the same as this function over here, then the limit as x approaches a of f of x is the same as the limit of this as x approaches a. And let's just be clear that I'm taking the limit of this entire thing. Okay, so those should be equal. Okay, so we can break this limit up across addition. That's one of the properties of limits. Okay, so we can take the limit of the first piece and then add it to the limit of the second piece. Okay, again, that's just a property of limits. Okay, the limit of this first piece plus the limit of the second piece, that's the same as the limit of these two added together. Okay, now the limit of this piece can be broken up across multiplication. That's another property of limits. So we can write this as the limit of the first piece times the limit of the second piece. And then the limit of f of a as x approaches a is simply f evaluated at a. And the reason that's true is because f of a is a constant. F of a is simply some number, and as x gets closer to a, it remains that same number. This does not depend on x. Okay, so x getting closer to a does not change this output. The output is simply f of a. It's a constant. Okay, so, and remember, the limit of a constant is the constant itself. Okay, so that's just f of a. Okay, and now notice that this limit right here, using direct substitution, this limit should be 0. Right? As x is getting closer to a, x minus a is getting closer to 0. So this limit should be 0. Okay, so 0 times whatever this limit is. Now, 0 times a number would be 0. But this needs to be a number in order for that to be true. So we need to make sure that this is a finite number. Now, if this goes to infinity or negative infinity or something like that, then we don't know what this is equal to. Okay, but as long as this as long as this is a finite number, then a finite number times 0 would give you 0. Okay, so let's just make sure this limit exists. As long as this limit exists and is equal to a finite number, then we have a number times 0 equals 0. But of course this limit exists because we know that f is differentiable at a. That is the condition of this theorem. And if you remember, f being differentiable at a means that this limit exists. This is the very definition of a derivative at a. It's this limit. Okay, and so we're assuming that f is differentiable at a, and that tells us that this limit exists. In other words, this limit is a finite number. Okay, so we know this is we know this exists. This limit exists. Okay, so it's a finite number. Okay, so a finite number times 0, right? This is equal to 0, gives you 0. And so we end up with 0 plus f of a, and that's just f of a. And wouldn't you know it, the limit of f of x as x approaches a is equal to f of a as long as this limit exists. Okay, we know this limit exists if f is differentiable at a, and that's why you need this condition. Now look, if this limit doesn't exist, right, if f is not differentiable at a, in other words, this limit doesn't exist, then you can't take that non-existent number and multiply it by 0. There's no way to perform this operation. You can only multiply finite numbers by finite numbers. Okay, so if this limit is infinity or negative infinity or simply doesn't exist and is not a number, then we have a problem here. And that's why we need this condition. We must have f be differentiable at a in order for f to be continuous at a. Okay, because we can't get this limit to equal f of a unless we get this to equal 0. And this won't equal 0 if this is not a finite number. Okay, so that proves it. That's the proof. Okay, so maybe just to finish this off, since this limit is equal to f of a, that implies f is continuous at a by definition. By definition of a function being continuous at a point. Okay. Okay, so that proves it. Now, one thing I want to mention is, in terms of pure logic, if someone tells you A implies B, then there's the contrapositive statement to this, which also must be true. And the contrapositive statement says that if it's not B, that implies that it's not A. And that's called the contrapositive statement. And hopefully this makes sense. If I tell you that A implies B and B does not happen, then A could not have happened, right? It's just not possible. A implies B, and you're telling me B did not happen, well then A didn't happen. Okay, and that's called the contrapositive statement to this statement. And I want to apply that, so that's just pure logic. Okay, I want to apply that to this theorem. So A implies B, A is this condition, F is differentiable at A, and then B is this condition. Or this conclusion, not condition, conclusion. Okay, so the contrapositive statement would be, well, if F is not continuous at A, then F is not differentiable at A. That would be the contrapositive statement to this theorem. And so we kind of have a follow-up theorem to this. this is kind of an alternative version of that theorem, which is simply the contrapositive statement of the theorem that we just looked at. So if f is not continuous at A, then f is not differentiable at A. And I'll give you a good example of this. Here's a function that's not continuous at A. And you can see it's not continuous at A because you have to lift up your pencil to draw it at A, to draw the graph of the function at A. So it's certainly not continuous at A, but why is it not differentiable at A? And the reason it's not differentiable at A is because in order for it to be differentiable at A, the limit has to exist as x approaches A from both sides. Okay, the very definition of a derivative is a limit, and it's a two-sided limit. It's the limit as x approaches A of f of x minus f of A divided by x minus A. So it is a two-sided limit. So you've got to approach A from both sides and get the same number in order for that two-sided limit to exist. But look, as you approach A from the right-hand side, you're not getting the same y value as you would when you approach A from the left-hand side. So that two-sided limit as x approaches A does not exist, and therefore f is not differentiable at A. Okay, and so it might be worth considering when a function is not differentiable at A. And so a function is not differentiable at A if at least one of the following conditions holds. F is not continuous at A, which we just mentioned. Here's an example of that, right? If f is not continuous at A, then it's not differentiable at A. So that's one possibility. It could be that f is not differentiable at A because f has a corner at A. So an example of that would be right here. That's called a corner or a cusp. It comes to a sharp point. The function is not differentiable at this point. Now, the reason it's not differentiable at this point is because the slopes of the secant lines on the left-hand side are approaching this tangent line, L1, whereas the slopes of the secant lines on the other side are approaching the tangent line L2. Right, you can see that. So as you approach this point from the left side, you're approaching this tangent line, L1. As you approach this point from the right-hand side, you're approaching this other tangent line, L2, and you're not approaching the same tangent line. So the slopes of these two tangent lines are different, and if you remember, f prime evaluated at A is equal to the slope of the tangent line at A. But you've got two different tangent lines here with two different slopes. Okay, they're not approaching the same thing from both sides. And therefore, the derivative at A, f prime of A, does not exist. Okay? Again, because the slope of the tangent line as you approach from the left-hand side is different than the slope of the tangent line as you approach from the right-hand side. Okay, so f is not differentiable at A because one of these three reasons, right? F is not continuous at A, f has a corner at A, or maybe f has a vertical tangent line at A. And so an example of that would be one of these two. So right here at this point A, this function is not differentiable. And here I think you can say that it's not differentiable because it comes to a sharp point. But it's also not differentiable because the tangent line that you're approaching from either side the tangent line you're approaching is actually vertical. And I think you can see that, right? It's approaching this vertical tangent line from both sides, and the slope of a vertical line is undefined. Okay, so f prime at 0 does not exist because that's supposed to equal the slope of the tangent line at 0. Okay, but the slope of the tangent line is undefined at 0 because it's vertical. It's a vertical tangent line. That also happens here as you approach 0. Notice that the tangent line begins to approach a vertical line as you approach 0 from both sides. Okay, so f prime of 0 does not exist, again because the slope of this tangent line is undefined. Okay, so again, f is not differentiable at a if at least one of these conditions holds. Okay, f is not continuous at a, f has a corner at a, or f has a vertical tangent line at a. Now, one other thing I want to mention before we actually do an example is notice that a function can be continuous at a, okay, and not be differentiable at a. And here's a perfect example of it. This function's continuous at a, but it's not differentiable at a because it has this sharp point at a. In fact, you should think of differentiability at a as a stronger condition. If f is differentiable at a, then it forces f to be continuous at a. So it's the stronger condition. Continuity at a is a weaker condition. You can have continuity at a, like you have in this example, but yet you don't have differentiability at a. Okay, so differentiability is a stronger condition. It's harder to satisfy differentiability at a than it is to satisfy continuity at a. And so that's one way to remember this. Okay, having said that, why don't we just look at example 7. Find the values of x in the open interval from -4 to 4 at which g is not continuous. Okay, so clearly it's not continuous at -2 because you have to lift up your pencil, and then you'd have to lift up your pencil at +2, so it's not continuous at +2. Okay, so it's not continuous at -2 and +2. Now find the values in this interval, the x values in this interval from -4 to 4, at which g is not differentiable. Okay, well, it's certainly not differentiable at this point when x is -2, and at this point when x is +2, because remember, if f is not continuous at a, then it can't be differentiable at a. Okay, so it's not continuous. It's not differentiable here or here because it's not continuous at those points. Okay, well, the other things you need to look for, right, if you're going to look for places where f is not differentiable at a, is you also need to look for any corner points. Well, you have a corner point right here. Okay, that's a cusp, comes to a sharp point. And so it's not differentiable at 0. Now it is continuous at 0, but it's not differentiable at 0. Okay, and the other thing we need to look for are any places where f has a vertical tangent line. Now this also has a vertical tangent line at x equals 0. I think you can see that the tangent line starts to approach a vertical line, or the secant lines approach a vertical line from both sides as you approach 0. Okay, and so it's not differentiable at 0, which we already knew because it also came to a sharp point at 0. Okay, now part C, let's sketch a graph of its derivative. Now remember, when you sketch the graph of the derivative, what you need to do is look at the slopes of the tangent lines at every point at g of x, in the domain of g of x. So the tangent lines here, okay, from -4 to -2, the tangent lines here appear to have a slope of like +1, right? This line has a slope of +1. So when you go to graph its derivative, g prime, you get +1 for the y value, which represents the slope of the tangent line for these x values between -4 and -2. Okay? And then right at -2, the derivative doesn't exist. And so that's why we have an open circle at -2. All right, and now when you go to the other side of -2, I think you can see that the tangent lines over here start off negative, and I think they become more negative, and then they really increase, well, they become more and more negative, okay, because they head towards a vertical line. So they start off slightly negative, and they become more and more negative. Okay, and so that's represented by this graph here, right? This is just below the x-axis, so it has a negative y value, representing a negative slope. And then those slopes just become more and more negative. Okay, in fact, it approaches negative infinity. Now notice at 0, this is actually a vertical asymptote, so g prime of 0 does not exist. It's undefined, and that's because you have a sharp point here, or you can say that the tangent line is vertical at that point. And so it has an undefined slope. Okay, now the values between 0 and 2, you can see the slopes are positive, and they start off being very positive, and then they become less and less positive until eventually they start to approach 0. Okay, and so you can see that's represented by this graph here, right? The slope of the tangent line is very positive, and it becomes less and less positive, and eventually it starts to head towards 0. But right at 2, the derivative does not exist, right? G prime of 2 does not exist because it's not continuous at 2. And so that's why there's a hole in the derivative right at 2, because that's not defined, right? G prime of 2 is undefined. Okay, and so then just finishing this off, between 2 and 4, you can see that the slopes of the tangent lines over here appear to be slightly negative, but then they become more and more negative, and they become extremely negative in here. Okay, and so the graph of the derivative, you can see that it starts off slightly negative, and it becomes more and more negative as you get closer and closer to 4. Okay, so this would be the graph of the derivative of that function. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.